All right, so the first thing I want to talk about today is that we won't have class on Monday the 29th. All right, so to make up for being here today, you guys don't need to be here Monday of next week. I'll be out of town. That's what's going on. Then what we're going to talk about today technically is polymer viscoelasticity. And this is the term we use to describe the fact that polymers are neither viscous nor elastic. They have elements of both. We've talked a lot about the elastic part, not so much about the viscous part. So we'll talk a little bit more about viscosity today. And again, to follow up, this table is very viscous. All right, the air is not very viscous. We measure them both in shear. All right, that's typically how viscosity is established. Not tension, not compression, but shear. All right, so we're all on the same page as far as what's high and what's low viscosity at this point, hopefully. And what we do is we look at viscosity, as it says here, as a concept that describes the intimate interrelation between elasticity, flow, and molecular motion. Of course, we talk a lot about molecular motion because that's what we've been talking about. And it turns out that a lot of things that we talk about at room temperature, like in terms of secondary bonding, also establish viscosity at 250 degrees. Right? So PVC at 250 degrees is going to have a higher viscosity than polyethylene at 250 degrees, or pretty much any temperature for that matter. All right, because of that secondary bonding. Secondary bonding doesn't go away just because we heat the polymer up. All right, it's still active, it's still important, it's still part of what determines how it resists the process of shearing. Okay, bless you. And this is also important from the standpoint of flow, because of course, as you'll recall, we're asking these polymer melts to move down these tiny little channels and go into these tiny little gates and fill some kind of three-dimensional feature. All right, and so those small passageways give rise, as you'll see, for plenty of opportunities for viscosity to build up and create what's called short shots, which means that instead of the 100% of what you want, you get 98% or 95%, and parts are missing that gets either put right back in the extruder or thrown away. Right? It's not useful. So one of the things we'll be talking about today is how we can change conditions to achieve a certain net result as far as shape is concerned, and what we might need to do in case there's a change in the raw materials. But first, a couple of other things that are related to that. We have stress relaxation and creep are two easily observed materials phenomena that we're all, I guess we're all familiar with creep, right? We've learned about creep usually for high temperatures for metals or ceramics, especially for ceramics, very high temperature creep. Metals are not so high temperature, but we, in those contexts, worry about creep at around 1,000 degrees or so. All right. With polymers, it can happen at room temperature. Okay. And the example I already gave you guys one about the biomedical, the acetabular cups. All right. How in the early days, before they knew about how important molecular weight was and cross-linking was, they had issues where the cobalt chrome head was creeping into the acetabular cup. All right, and so basically the polyethylene was being tunneled into by the cobalt chrome head. All right, and that was because they didn't really appreciate the fact that at 37 degrees, polyethylene creeps. All right, unless you crank up its molecular weight and cross-link it, it's going to creep. And so the other thing, though, that we're not as familiar with is the concept of stress relaxation, which involves the circumstance in which you rapidly stretch a sample to a specific length and keep it stretched to that length. All right, so first off, assuming that it doesn't break by rapidly stretching it, we know that it arrives at this new dimension. We forced it to undergo strain, and it should make sense to you at this point that the polymer is going to respond. Given the time sitting there at that higher level of strain, it's going to respond, and it responds via this process of stress relaxation. So we put the polymer chains under stress, and then they're at this new value of dimensions, and given time, they'll try to rearrange themselves. All right, and that can change the net stress in the sample to make it lower. Okay, to boost up entropy. All right, and decrease energy. Creep is more familiar to us again. A constant stress is applied to a polymer sample, usually at room temperature. The net deformation or strain increases with time. And so we have a cube, we apply a load onto it, and that cube starts creeping down into a rectangle, all right, over time when we put that weight on top of it. All right? Does that all make sense? All right, that's the one we kind of know. And what we are trying to do in the context of today's lecture is first off talk about the time temperature superposition principle. And it turns out that creep and stress relaxation are going to be dependent on both time and temperature. Shouldn't be a surprise. Both are governed by molecular motion. All right, so everything that contributes to molecular motion is also going to play a role here in terms of creep and stress relaxation. Higher temperatures, of course, give us greater chain mobility, and that means that the chains can move around faster and can give rise to higher levels of molecular motion. So polyethylene will creep more at 48 degrees than it does at 37 degrees. Right? This should not be unusual in your eyes. Increases in the time of exposure allows continuous molecular motion and allows the polymer to respond. And the question that we're asking here, is there a relationship between temperature and time that accounts for molecular motion? Yes and no. What we have to try to fill in that gap is what's called the WLF, or Williams-Landau-Ferrier equation. And in this context, we find that the log of viscosity, or eta, all right, at any given condition, the ratio of that, take the log of the ratio of that versus the eta value at the glass transition point itself, meaning that at some low temperature, as it goes from being one to the other, that's going to be equal to this entire equation on the right-hand side, 17.44 times the difference in temperature, so the delta T above TG. We don't care about below TG because that's glassy material. That's not viscoelastic at that point. So only above TG is this operative, divided by 51.6 plus, again, that delta between whatever temperature we're at and the glass transition temperature. All right, so that's kind of the initial reference state. And for reasons that will hopefully become clearer later, we generalize this as log of eta, a log of the ratio of eta divided by eta at some reference temperature. It can be glass transition temperature, it might be something else, depends on the data that's going into this relationship. And again, it's 17.44 times the differential in temperature, T minus T naught, divided by 51.6 plus T minus T naught. And it turns out, and you'll see an example of this in a minute, that we can also look at time as far as the superposition principle is concerned, and that is also equal to this ratio of the two viscosities over each other, the log of the ratio of the two viscosities. Okay?
Something I always ask when I see like a multi-hyphened equation like this, do these two people like work together to develop it, or they just kind of happen to stumble on the same thing at the same time?
Multi-hyphen? Oh, you mean the many names?
Yeah.
Ooh, I think that was a single paper published by all three of those authors. Yeah, that's where that came from. I did look that up at one point. Any other questions? And so we have what's called the time temperature superposition principle for the test temperature, T, which is greater than glass transition temperature, and which is equal to those three expressions, or set equal to each other. And so it should make sense that if temperature decreases, then the log of these ratios will increase, all right, because these values in the delta T are going to change substantially, and it turns out that the denominator is more dominating. Similarly, if T increases, then the log of those ratios also increase, okay, and that hopefully also makes some sense. So in other words, by changing either temperature or time, we can achieve the same viscosity target if that's what we're wanting to do. And so an example of this is a one-year aging experiment performed at a certain temperature. The net result will require less time to achieve if it is performed at a higher temperature. There should not be anything phenomenal to you about that. And so this superposition principle for viscoelastic materials, time and temperature are equivalent to the extent that data at one temperature can be superimposed on data at another temperature by shifting the time. Okay, so you can get to the same endpoint with two different approaches, either increasing the temperature or letting it sit there for longer periods of time. Okay, and unlike a lot of other things, those are kind of equivalent in polymers. It actually works pretty well. You can go back and forth. Unlike a lot of other simulated aging processes that don't work well if we try to increase the temperature. Alright, so an example, if we test the glass transition temperature using DSC, and we just talked about this last time, if we use a slow heating rate, achieving any particular thermal transition, either TG or TM, requires a longer time, and this then also means that there's more potential for artifacts as a result of that. And if we use a faster heating rate in achieving any particular thermal transition, either TG or TM, requires a shorter time. And there's also potential for artifacts there. This refers to the fact that there's a lag in some cases if you go really fast between what the machine is applying to the polymer and what the polymer itself is experiencing. That's what I'm getting at. And what we can do in this context with the time temperature superposition application is develop a master curve that can be created, that can be applied to other temperatures and conditions. So we're going to talk about temperature and viscosity today and time, but there's another whole series of equations that relate to prediction of viscosity at different temperatures. But we can also look at mechanical properties, elastic modulus, which you guys are all familiar with, and then we also have things that people are generally less familiar with: storage modulus, the derivative of the storage modulus G prime, and the derivative of the storage modulus G double prime. And this is all stuff that you should have learned from Dr. Sayre, or at least those of you in MSE. You may have seen this before, right? Yes? No idea? No one knows who J. Sayre is?
We had him for a lab once.
You had him for a lab once, yeah, right. He talked about some of this in the lab, didn't he?
Maybe.
All right.
It
Should have.
for vacuum sealing of polymers.
Oh, wait a minute. So that's not the 33.
It was one of Elton's labs. It was like the first.
Yeah, there's like one section of a lab.
Okay, so one of Elvin's lab does this now. Okay, so Jay helped set that up, and I guess Elvin's just taking it over. Yeah, okay, all right. Yeah, that's the lab I'm referring to. So Jay doesn't come in and lecture on that one anymore?
I think he did. It was like a day.
Elvin like brings in like lecturers, and they would do like either a Zoom session for one day or like discuss it for us with us at the lab.
Okay.
He talked a lot about how he destroyed a machine for like Battelle.
Yes.
He destroyed a machine for Battelle.
Because he forgot to turn the vacuum pump or something.
He what?
He forgot to turn on like a vacuum pump or something and ruined the vacuum pump room. And it got like resin in it and it just died.
Okay.
And then he had to explain to his higher ups why he lost like a multi-$1,000 vacuum pump.
Okay. All right. Well, anyway, what he's supposed to talk about are these things involving DMA experiments, which we can now do. And I guess you guys didn't do any from the sound of it. All right. Well, anyway, but that, getting back to it, these mechanical properties can also be applied using these same superposition applications. So you can do the same thing we're talking about, but look at mechanical properties as well. So when we think about viscosity, and this is kind of speaking really broadly here, we talk about viscosity of polymer melts, more of the physics polymer melt definition. There are 5 regions of amorphous and linear. Most polymers, polymer behavior. We have the glassy region, all right, and in many cases we don't particularly worry too much about the viscosity there because we're not using polymers under those conditions for the most part. And then we have the glassy transition region, which is probably more important because in some extreme cases we can actually look up at the viscosity of those materials. Usually these are pretty high strength applications. The majority of what we work with, though, involves the rubbery plateau region, so this region here, which is above the TG, and then the rubbery flow region, and then a lot of what we're talking about really involves the liquid flow region. And this is where the chemical engineers take over here typically, where they describe all of these fluids, all of these different bonding circumstances as this gray continuum with no real discernible characteristics. They just say it has this rheology, and then we go to town with rheology. But Anyway, so that's a lot of what we're talking about, because this is where we start to make things. All right, we can kind of make things if we want to really, really badly in 3 and 4, but region 5, where it actually becomes a true engineering melt as opposed to a physics melt, is where we actually start to ask questions about how can we achieve different cycle times, different raw materials, et cetera, et cetera. So hopefully that makes sense.
So,
No?
Never mind, I was looking at something else, so.
Okay. All right, so in region 5, linear amorphous polymers are capable of what's called extensive flow. And we'll talk about what that means in a second, but that's where the polymer chains get stretched out during the flow process, and that's where a lot of these viscosity relationships become applicable. And so in this context, the melt viscosity eta can be calculated using the WLF equation. Again, this relationship that we've talked about previously. And the parameters 17.44 and 51.6 should vary with the polymer being examined. Not always. So in a lot of the problems I'll ask you to work, or you'll be working, we just work with 17.44 and 51.6. But if necessary, we can use the parameters C1 prime and C2 prime. And so this table, which of course I would give you, gives you some WLF. I give you a less fuzzy version of that table. Wow. Gives you parameters for C1 prime and C2 prime, which in some cases can differ substantially, but in most cases are not all that different from those previous values of 17.44 and 51.6. So the rule here in general, though, if I don't give you those values, then we just end up using 17.44 and 51.6. Okay. Any questions about that so far? All right, so an example problem to show you how this works. A polymer has a glass transition of 0 degrees centigrade, which is reasonable for a lot of things that we deal with engineering-wise. However, at 40 degrees centigrade, it has a melt viscosity of 2.5 times 10 to the 4th Pascal seconds. Now, a word of caution about viscosity and Pascal seconds and pascals is that it's a chemical engineering term. It's very important, but you as a individual can't really look at something and say, oh yeah, that's about 15 pascals. You can't, we just don't have the ability to do that. So don't try to get some feeling for viscosity values, all right? It's just, it's not something that is easily picked up. It's not, unlike, we talk about feet per second and things like that. We can sort of get an idea what that means. But pascals, it's just, we don't have enough familiarity with viscosity to really say, oh yeah, this is about X pascals. And so the question becomes, what will its viscosity be at 50 degrees centigrade if the values of C1 prime and C2 prime are the usual suspects, 17.44 and 51.6. What was it on? My wife was watching an NFL football game yesterday, and they said something about the running back did a Kaiser Sose. And it's like, man, that's an obscure reference. Does anybody know what that means? No? All right, so there's a movie called The Usual Suspects. All right.
Never seen it.
Okay, all right. There's a character of Kaiser Sose who turns out to be right in front of them the whole time. Anyway, and I was just like, okay, so none of you know it either, so it's just a really obscure reference. Like, where the hell did that come from? Anyway, so if we calculate first off the glass transition or the viscosity at the value of the glass transition. All right, so we get this as our reference point based on the data that's available to us using these equations. And so we know that the log of eta at whatever condition is equal to the log of the ratio of eta to eta Tg is equal to this overall expression, and we need to rearrange things. And so this is where you guys need to go back and brush up on how to work with logs. All right. So you can take this ratio, break it up into two separate values, one minus the other, and then move it over to the other side of the equation. All right, this all sounds familiar. If you haven't seen it in a while, you might want to brush up on how that works, because these kinds of manipulations you should be able to do. They're not all that hard. So given the fact that we have this value of 2.54 for end at 40 degrees centigrade. Then we're trying to figure out what the log of eta sub Tg is, and we have these two temperatures, 40 and 50. Keep in mind that when we work with these values, and I get this every year, these values are computed in Kelvin, all right? So I may give you the information in centigrade. Make sure you convert it to Kelvin before you plug it in to these equations, okay? Yeah?
If you're to be given difference, does it really matter?
It does in this case because it's 40 and 50 as opposed to 313 and 70. Now, it may not matter always, but it matters ultimately that you do it that way.
But you're always subtracting.
Yeah, but other problems we'll talk about later. It's going to be a problem if you do that. So just religiously convert is the point I'm trying to make here. And so we know that log of eta sub Tg is going to be equal to 13.013. And then we, again, using the inverse value of logs, we have a melt viscosity about 10 to the 12 Pascal seconds as Tg. This is quite reasonable. All right, it's a really high value. 10 to the 12th of anything is pretty darn high. That's not unusual. And so then we calculate the new viscosity at 50 degrees centigrade. So the log of n is equal to this 13.013 minus this relationship now 17.44 times the quantity 323 minus 273 divided by 51.6 plus 323 minus 273. This is equal to 4.43. Again, inverse log of that is 2.69 times 10 to the third Pascal seconds. All right, and so we now know that if we go from 40 degrees centigrade to a higher temperature of 50 degrees centigrade, the viscosity is going to drop from the original value of 2.54 to 2.69 times 10 to the third. And so again, these are abstractions, but when it comes to how well a material flows down a tiny little channel, it heads to a tiny little gate that goes into making our part, these values are actually very important as far as process control. Okay, any questions about that? Okay, so more information. And we talked, well, let's see, did we talk about that? We talked about it a little bit once or twice. Many were talking about branched polymer chains. But in the context of melt viscosity, as you just had an example of, decreases as temperature increases, and the status of the chains within that melt will affect the viscosity. And the topic at hand here involves molecular weight. And so you should already know that as we increase molecular weight, viscosity goes up. As we decrease molecular weight, the viscosity goes down. If chains are able to move easily, the viscosity is low. If they're entangled, i.e. they are above a certain molecular weight, all right, in which entanglement becomes an issue, the viscosity is significantly higher. And polymer chain entanglement is related to chain length, of course. Long polymer chains, high molecular weights obviously tend to become more entangled. Again, shouldn't be a big surprise. But as it turns out, this is one of the issues, and we'll see some consequences about involving this in a minute, that higher molecular weight polymers can have a much higher melt viscosity than lower molecular weight polymers at the same temperature. All right, so this is one of the limitations that keeps molecular weights low for some particular products. We talked a lot about molecular weight, M sub n, M sub w, polydispersity. But if your molecular weights are very high, you're not going to be able to make a lot of things using tiny channels and tiny gates. I talked about the example of the acetabular cup. You just have a glob, and you put it in the mold, and you squish the glob. All right, it's not delivered to that mold. You have to drop it in the mold. Here we're talking about, can we mold something using tiny little channels, runners, etc., gates and so forth, or not? And so the question becomes, what is the critical molecular weight for polymer chains to start to entangle? What is the critical chain length? And we gave you that example for polystyrene, if you remember that, where it goes up to a certain value and then the mechanical properties change dramatically beyond a certain value of molecular weight. All right, that's kind of the same, in this case, a viscosity version of the same type of behavior. And so we define this chain length ZW as the number of atoms along a polymer chain backbone. All right, and so this, of course, will depend on how many atoms are in the side groups. Okay, so you have to keep that in mind as well. But in this case, we then have this relationship which shows us that below this value of log z sub cw, we have one slope, which is about 1 here, and then as we go above that value, we get to a much higher slope of 3.4. All right, and that's you see that in these two equations. So when z sub w is less than this critical chain length, we have this viscosity is equal to the factor k sub l times z sub w to the 1.0 power. When z sub w goes above this critical chain length, it becomes the same relationship, except it's k sub h z sub w to 3.4. All right, and so what that tells us is that things become much more difficult, all right, much more quickly at higher molecular weights. And so we can make really high molecular polymer chains, but can we actually injection mold them becomes the issue. So we may have phenomenal properties at a molecular weight of 1,000,000, but there's no way we can make that polymer chain go down a tiny channel because of this relationship. Right? The viscosity just jacks way up because of all those entanglements associated with those higher molecular weights. All right, so there are limits here that get us beyond this point a little bit, but then after that, you forget about it. You're not going to be able to mold that using injection molding. You have to use some other process. Does that make sense to everyone? And so we know that many polymers have these critical values of molecular weight, or Z sub C, in the range of 600 plus or minus 200. And Z sub W, of course, is proportional to molecular weight. Z sub W corresponds to a critical molecular weight MC prime, and MC prime for common polymers. Again, I apologize for the fuzziness of this, but for polyethylene, we're looking at 4,000. All right, and then polystyrene, 31,000, and then lots of less than 10,000s, around 10,000 values for many different polymers that we're familiar with, and then a whole bunch of these are well below 10,000. All right, so these are not high molecular weight polymer chains. However, they are moldable. And so for making something that's small and cheap, and we make a whole bunch of them, we're not going to expect these to bear a whole lot of load or be all that resistant to creep, but we don't care. If it's a kid's toy, so what? If it's a piece of the pen you're using, so what? It doesn't have to see or withstand a lot of stress, but it can be molded that way relatively cheaply because the molecular weights are lower. All right, now again, keep in mind this leaves out any additives. All right, we'll talk about additives in a minute, but this is by itself in pure systems. These are the limits. Now we add in, we'll talk about lubricants, plasticizers, colorants, and things like that can make it go the other way. But anyway, we can extend this range by putting in additives. Is what I'm getting at. We'll talk about that in a second. All right, any questions about that? And you can see one thing to point out, that polydimethylsiloxane, remember how bendable and so forth PDMS is, that because of those characteristics we can get to higher values of molecular weight if we wanted to mold PDMS.
I'm pretty sure I know the answer to this question, but are we supposed to memorize any of these?
Nope. No, but you're supposed to appreciate them. All right. Any other questions? All right. So, now let's get into an example. You are the engineer in charge of a polystyrene drinking cup manufacturing unit. So I heard a piece of a song the other day. Toby Keith Toby, some country singer.
Toby Keith is a country singer. I'm from Texas. I know him quite well.
Okay, so he has some song about solo cups.
Red Solo Cup?
Red Solo Cup, yeah. And he says it decomposes in 14 months or something like that, which is a bunch of crap. It's like 450 years for a red Solo Cup to decompose. It's polystyrene, all right? And we know polystyrene is pretty resistant to a lot of things. So even that thin red wall will take 450 years to decompose, and that just turns it into fragments. All right, so Toby Keith is wrong. I hope you're not getting your technical data from Toby Keith. But anyway, so if you're an engineer in charge of making these cups, normally, this is kind of a what if, you process the material at 160 degrees centigrade, which is not too bad in the scheme of things, where the viscosity is 1.5 times 10 to the third poise at this Z sub W 800. However, today you've been asked to use another polystyrene having a Z sub W of 950. Why might someone ask you to do that? Cheaper. Bingo. Yes. All right, you knew the answer as well. So, yeah. All right. It's cheaper to make. It's usually not because of properties. We like to think that would be the case, but it's usually because it's cheaper. All right. So if somebody found some polystyrene from some other vendor, and they say, "Here, try this." And so, what changes in processing temperature will allow you to bring the viscosity back down to 1.53 times 10 to the third poise? That's a viscosity we're used to. That's a viscosity that travels down the gates and runners and so forth. So we want to get back to that viscosity so we can keep making money using this process. And as you've heard a lot lately, the TG for polystyrene is 100C. Now, of course, we're ignoring whatever additives are making it a red solo cup and so forth. But anyway, and of course, unsurprisingly, in the real world, both Z sub W's are above that critical value. All right, so we're in the 3.4 range, which is really sensitive to these issues, so we have to worry about that. So we use that expression as opposed to the 1.0 expression, K sub H equals Z sub W to the 3.4 power. K sub H then, given all the data at hand, is going to be equal to 1.5 times 10 to the third, that viscosity value, divided by 800 to the 3.4 power. So we set K sub H as 2.02 times 10 to the minus 7th, and this is again at that temperature of 160 C. The viscosity for Z sub W at 950 at 150 C, again using the same expression, we plug our value of K sub H that we just figured out, and Z sub W to the 3.4, so it's 2.02 times 10 to the minus 7th times 950 to the 3.4 power. This is 2.69 times 10 to the third poise, all right, so it's above where it was, which we're not happy about. And so we want to figure out, okay, what kind of change in temperature will get us back to where we were before. That's what we're really all about. And is it a reasonable change in temperature? So we calculate A to sub G for a polystyrene with a Z sub W of 950. And so we have the log of these two viscosities, the viscosity N versus the reference glass transition viscosity. Again, using this now familiar expression of 17.44 times the temperature differential divided by the quantity 51.6 plus the temperature differential. So we have log of 2.69 times 10 to the third, this value up here, divided by that viscosity value. And so we need to go back and determine what that viscosity value is, knowing these changes in temperature. And so we get this reference point 6.39 times 10 to the 12 poise, which is a crazy high viscosity. We're not molding at that point. We're just using that as input. Okay, so it's not a practical term, reference term that we have to solve for. And so what we then do is we plug in this value that we just figured out for the reference state viscosity at the glass transition temperature, and that is divided into 1.5 times 10 to the third, and the log of that can then be used to help us solve for that new temperature that we're trying to figure out. Okay, so all these equations are interlinked, and so as opposed to 160, we're now operating at a temperature of 163.6, which is not too bad. All right, an increase in temperature of 3.6 degrees, 4 degrees Celsius shouldn't be a problem. I wouldn't say that it's never a problem. I would worry about your colorant. Your red solo cup may end up being a garnet solo cup by the time you're done if the temperature changes 4 degrees centigrade. Things like that can happen. But in general, everything should be fine, at least equipment-wise. Any questions about that? All right. So you just need to be familiar with the rules, how logs work. Okay, make sure everyone understands how logs work. And then you can solve for these things. So the WLF equation and the relation of viscosity and Z sub W or MC prime are very important for polymer processing, especially for the many potential problems related to simultaneous changes in temperature and molecular weight. Okay. Important that any extrusion of polymer melt machinery can function efficiently at the same melt viscosity and the new higher temperature. Polymer and additive stability, which is probably really what you have to worry about, also has to be considered. So, your machinery, 4 degrees centigrade, no big deal for the machinery. 100 degrees centigrade, that's a problem. All right, you don't have a lot of wiggle room with these pieces of machinery, but especially additive stability, that becomes a real issue as well. Any questions about that? Yeah?
Are you more concerned with the additives like pH rising or like evaporating out?
I'd be concerned with the additives no longer functioning at those higher temperatures. I'd be concerned about the color becoming something else at higher temperatures because they're only rated to a specific extrusion temperature. You go above that, then they start to oxidize or break down or cross-link. All kinds of things can happen. Any other questions? All right, and so this allows us to also talk about polymer rheology in a way that deals with this extensional flow and why that's so important to us. So again, we're talking about these very tiny pipes that these flows have to go through. And when the pipes are that tiny, it's a lot of interface for the polymer to flow down. And so rheology is the study of stress and deformation of liquid or viscous matter. And again, our brethren in chemical engineering, they start from here and go far, far beyond it. But we're just going to talk about some of the fundamentals of rheology that determine why this is such a difficult problem to solve for us. And so this usually deals with polymer liquids, both melt and solutions, under shear. Again, that's where we measure viscosity in shear. And this is a specific mechanical stress state. And we think about the flow down those tiny pipes. And so we have this flow profile that you definitely need to understand, in which we have a maximum in the flow rate in the middle of the tiny pipe. And then at the edges, what is the flow rate? What is the velocity at the edge? 0. All right. So it's a polymer melt in contact with a wall, and what's in contact with a wall is not moving. It's stuck to the wall. All right. Does that make sense to everyone? In this very pure system that we're talking about here, those polymer chains that are on the wall are not going to move. And so what that means is there's a tremendous amount of shear between the center and the edges of these materials. And that's represented by these gradients in arrows. So we know the arrow is 0 here, it's slightly more than 0 and so forth, but in that transition from here to here to here to here all the way to the middle, there's shearing going on. All right, and that's why we think about viscosity as being the control factor. It goes to a maximum in the middle and 0 at the edges. Does everyone believe that? All right, it's a reasonable set of assumptions. Of course, we can affect this with additives and so forth and so on. And so that's the velocity profile. And then we have what's called shear rate. All right, and so it should make sense to you that shear rate is a maximum at the edges and a minimum in the middle. All right, everything's kind of flowing relatively smoothly in the middle, and the shear rate that's involved in that core region is pretty small. It goes to a maximum at the edge, where the change in the velocity is at its greatest. And then, unsurprisingly, we have the term shear stress, which is the amount of this shearing stress that the polymer chains are experiencing. Again, a minimum in the middle and a maximum at the edges. Any questions about that so far? So this is where I start talking about additives. So of course, and we've already talked about this, you guys remember the example of lubricants, right? And so what we do is we get that external lubricant in there, and it precipitates out on the walls, all right, as a discrete low molecular weight compound that separates the chains from the walls, or at least tries to, all right. And so that makes these values smaller, and then it means that these values of velocity are going to go up in the presence of that lubricant. All right, so we try to free the polymer chains that would normally be at 0 to something that's greater than 0 due to the presence of this lubricant on the walls. All right, so now you should see why these lubricants are so important, because they make this possible. They act like rolling ball bearings of short chain matter, so the polymer chains themselves don't have to do all that work. So very important additives in these systems. Okay, any questions about that? I'm not sure why this shows up twice. Okay, And we also talked about internal lubricants. Okay, those form these little pools that make the internal viscosity smaller. So flow is also easier there in that context. Under shear flow conditions, polymer viscosity is called shear viscosity. We can define shear viscosity as a ratio of the imposed shear stress and the shear rate. So this value of eta is equal to tau divided by the shear rate. For very different fluids, we have Newtonian fluids. And so the one we're all familiar with, which is what gets people in trouble, is water. All right? And with water, viscosity does not change with shear rate. And so we talked about the example of, we have a sink full of water, it's very tough. No matter how fast we hit it, the viscosity of water does not change. All right, that is a Newtonian fluid. However, I guess also, if we look at that, the standpoint of shear stress versus shear rate, that has a linear profile. All right, it doesn't go to some value of 3.4, for example. All right, it just has a linear response. And so we're all familiar with this, and it's totally wrong when you talk about working with polymers because none of them behave like that. With these non-Newtonian fluids, e.g. all polymers, we have a nonlinear relationship in shear stress and shear rate, i.e. the shear viscosity is dependent on the shear rate and the shear stress. We have two potentials. We have shear thickening, where the viscosity goes up as a consequence of an increased shear rate, and we also have shear thinning with polymers. We can have both with these plastic systems. Shear thinning is typically a better thing to have than shear thickening, but you can work with both if needed. And so we see, as a consequence of shear rate, increasing shear rates, we have different behaviors in terms of shear thinning and shear thickening. So unfortunately or fortunately, most polymer fluids are non-Newtonian. Most polymer fluids are shear thinning. Viscosity decreases with an increase in shear rate. And it sounds good, but you're paying more money to make that happen, all right, to get the shear rate up that high. So it's not always the fix you might think it is. A few polymer fluids are shear thickening. The viscosity increases with an increase in shear rate, and these can be particularly problematic to get to mold something out of because of the fact that viscosity is increasing. And so we look at these different relationships for how strain rate influences shear stress. All right, and these are the stress that's being placed on those polymer chains, which we bring in lubricants to decrease that stress, but by themselves we have the Newtonian fluids that we're all familiar with that don't actually exist in these polymer systems, and we have shear thickening and shear thinning behavior, and again the slope as before is going to be the viscosity. So that should all be familiar. And it's important to note that shear thinning is related to the alignment and disentanglement of polymer chains. All right, and so if we have these polymer chains in these structures, and the question becomes how entangled are they and what happens when we apply stress to them. And so if we have polymer chains that sort of look like this, where they're more or less randomly oriented, these are going to give us a lot of viscous entanglements with their neighbors. So again, going back to that velocity curve, so they're all in shear with each other. And so if they look like this when they're shearing with each other, we're going to have high viscosities because there's entanglement going on with that shearing between the different layers. But if we can get them to align, then we can get lower viscosities because now the polymer chains are able to slide past each other more easily. All right, so the shearing process is easier when they're lined up. Does everyone see that? And so ideally it's just the side groups brushing past each other rather than polymer chains entangling with each other. And so when we have a polymer with entanglements, we get a higher viscosity. Increases in shear rate can lead to disentanglement, chain stretching, and decreased viscosity. All right, and so this is part of the process of injection molding and understanding what your particular polymer system can do. All right, linear polymers can do this. Branched polymers, people don't like to work with because they tend to get stuck in this mode, for example. Right? So another reason to not have branched polymers in your system. And the saying exists is that polymers love shear. During processing, higher shear rates yield lower viscosity up to a certain point. Lower viscosity makes processing easier in this context. Lower viscosity can be achieved by adding processing additives in to make that process easier as well. Okay, any questions about all that? So we understand that shear is how we measure viscosity. Things that are difficult to shear, like this desktop, are going to have high viscosity. Air is a low viscosity. All right, and polymer chain structure controls response to shear, and low molecular weights can align more easily, giving us lower viscosities as well. All right, so do we have class on Monday the 29th?
No.
No, we do not.
Well, at least you won't be here.
I won't be here. You guys can show up and talk to each other if you wish. But
What you doing on the 20th again?
I'm out of town. I'm up north.
Enjoy your trip or whatever it is you're doing.
Yeah, it'll be different.
Work conference or vacation?
It's a vacation kind of thing.
Where are you going?
Up to Ashland.